We've looked at vectors in 2 dimensions where we had an x component and a y component, but real life there's vectors in space where we have 3 dimensions, where we have the x, y, and z plane. So we're going to apply everything that we learned in 2 space to 3 space. So the first thing is, how do we find the distance between 2 points given 3 dimensions? So if we plot a point -2, 2, 3, so that means we would go -2 in the x direction, +2 in the y direction, and up 3 in the z direction, and that's point A. And then follow the same thing for the second point. We would go 4 in the x direction, 3 in the y direction, and then below that plane negative, and this would be point B. So what we're trying to find is the distance between those 2 points. The good news is that it's still the Pythagorean theorem, just expanded through to 3 space. So let's go through just doing the math. So the distance is going to be the square root of, we're going to subtract the x components, so 4 minus a minus 2, that would make that plus. Then we'd have 3 minus 2, and -3 minus 3. You just want to keep your order consistent. So we would have the square root of 6 squared, and 1 squared, and -6 squared. So that would be 36 plus 1 plus 36, so we would have the square root of 73. And that would be the distance between those 2 points. This is a demonstration written by other math people. They're writing it in using a Wolfram or Mathematica. This particular little demonstration lets you take 2 position vectors or 2 points in space, plot them, and then you can see them in relationship to each other. And you also can drag this around and rotate it, and so you can really see it, because it's very difficult to plot 3 dimensions on flat paper. So just like in vectors of 2 space, we're then going to find the position vector. And a position vector just moves the points where one of them is at the origin. So if we want, if P1 is the initial point and P2 is the terminal point, then the vector connecting those 2 points is called the position vector. And it is always terminal minus initial. That is very, very important, because vectors have a direction. So that is different than that. So how do we find that position vector given these 2 points? Well, we would have 4 minus a minus 2 in the I direction, 3 minus 2 in the J direction, and -3 minus 3 in the K direction. That should look very familiar. That's exactly what I did when I was finding the distance. So I would have 6I plus 1j minus 6k. You might recall when we were doing the vectors in 2 space, we also could write them in what was called component form with those little brackets. So we could write it as 6, 1, -6. So if you get tired of writing that I, j, and k, that is an alternative way to write the vectors. So now how do we find the magnitude? If vector v is ABC, then the magnitude of a vector is the distance or the length of a directed line segment. Remember, direction, very key to a vector. And the magnitude is defined to be just that. Remember, in 2 space, it was the square root of a squared plus b squared. So it comes from that distance formula, the Pythagorean theorem. So how could we find the magnitude of v, which is P1, P2, which happens to be from the previous example that? So the magnitude would be a squared, which would be 6 squared, plus b squared, which is 1 squared, and c is -6 squared. Does this look familiar? It should. It's the same thing as finding the distance between the 2 points. Another thing we did in 2 space was find the dot product. It was very easy. Remember, the dot product, we're just multiplying the I components and then we're adding it to the product of the j components, and now we have a k component that we're just going to add on. Recall the dot product is a scalar and not a vector. So you're going to just end up with a number. So if I want to find v dot u, I would multiply 2 times 1 and add it to negative 2 times 3 and add that to 1 times negative 4. So just doing some simple arithmetic and hopefully not messing up, I believe you get negative 8, which is a scalar, not a vector. Now I'm going through this fairly quickly because we've already done it in 2 space. We're just adding that third dimension. Another thing we found in 2 space was the angle between the 2 vectors. It is the exact same formula that we also talked about. Right, so if we want to find the angle between these 2 vectors, how do we do that? Well, first of all, we need to find their dot product, which we've already found to be negative 8. We need to find the magnitude of each vector. Remember, that's the square root of the component squared, so we have 2 squared, negative 2 squared, and 1 squared. Now that happens to be the square root of 9, which is 3. And so let's see, the magnitude of u, so we would have 1 squared, 3 squared, and negative 4 squared. And again, checking my arithmetic, I believe that's the square root of 26. So if I want to find the cosine of theta, the dot product divided by their respective magnitudes. Now, just like on the 2 space vector, you want to be very careful about punching that in to your calculator. All right, so I've checked to make sure that my calculator is in degree mode. I'm just going to go ahead and do this arithmetic right here. So I have negative 8 divided by, this is where you need to be careful, parenthesis 3 times the square root of 26, and I've got to close the parentheses twice. Right? So the cosine of theta is approximately negative 5.5229. So theta would be the inverse cosine of that previous answer, so I'm just going to use that button. So theta is about 121.5 degrees. So again, just be careful of punching that into your calculator when you're dividing by a product or some other thing besides a single value. Make sure you put parentheses around it in your calculator. And one of the last things we did in 2 space was to find a unit vector. Recall that a unit vector is a vector that has length or magnitude of 1. Unit is 1, just like on the unit circle in trigonometry, the radius is always 1. So we defined it in 2 space that for any non-zero vector, the unit vector is this. What does that mean? You're just taking the vector, the given vector, divided by its magnitude. We're just taking some vector and dividing it, keeping the same direction, so we have that length of 1. So what do we need to do to find that unit vector? Well, the first thing, let's look at its magnitude. Let's see, I believe that's 81 plus 9 plus 1, so that's the square root of 91. So the unit vector in the direction of v would be the vector, and I'm going to go ahead and write that in component form, divided by its magnitude. You could leave your answer like that. It's ugly, but it's okay. You could maybe write it out in front, or you could go ahead and distribute that. And then some books or teachers are going to go ahead and make you rationalize that denominator. I'm not. So you could leave your answers like that. You could also go put it in the IJK format. So again, this is just a repeating of the process from 2 space to 3 space.